In this video, I'm going to be introducing the concept of limits. This video lecture series is going to be covering the basics of differential and integral calculus. Now, I'm going to start with the assumption that people watching these videos have a familiarity with trigonometry and algebra. I'm going to assume that you are familiar with these concepts. So this video series is like starting with what would be a first semester college calculus. My eventual goal is to get into all sorts of physics. I think that the problem with a lot of physics is that it's not very accessible. And part of the reason why it's not very accessible is because it's hard to get a hold of information that's aimed at the demographic that this lecture series is aimed at. Most of the information on physics is either a completely non-technical treatment, as you would find in popular science books or on television, or it's a treatment which already assumes that the individual reading it is either a graduate level or postgraduate level, so in other words, already either an expert or a near expert in the field. So this is aimed at people who want the real depth of physics, but they don't already possess the machinery. And part of really understanding physics is mathematics. You can't understand the true depth of physics without understanding the underlying mathematics behind it. Because as we've been shown, especially in the 20th century and this early part of the 21st century, is that nature is not, for the most part, intuitive. We see that nature does not conform to our intuitive expectations. Newtonian mechanics can relatively make sense on an intuitive level to us, but the real underlying deeper physical principles like general relativity, even special relativity, and quantum field theory, standard model, none of this stuff can really fully make sense at an intuitive level. Even the physicists who study it their whole lives have to somewhat suspend their attempts to view it intuitively. The mathematics is really fundamentally necessary to understand it. So let's get started. All right, now what is a limit? Because essentially calculus, what makes what is traditionally referred to as calculus different from ordinary algebra is really the addition of the concept of a limit. Let's start with an example. The limit as x approaches 0 of 1 over x. That's how you would read this notation here. Now, what does this mean? Right here, you have a particular function or relation of some sort. Right here, this just denotes that you're talking about a limit. This denotes the value that you're approaching. All right. Now here we have a function of x, namely 1 over x. And what we're really asking with this notation here is what happens to the function 1 over x as x gets infinitesimally or arbitrarily close to 0. As x gets closer and closer and closer to 0, how does the function 1 over x behave? Now, we're not asking what the behavior is exactly at x equals 0. That's not our concern. That's not what a limit takes into account. For example, the function x equals 1 over x if x does not equal 0, x equals 5 if x equals 0, f of x, the function f of x equals 1 over x if x is not 0, f of x equals 5 if x is equal to 0. That function has the exact same behavior for its limit as x approaches 0 as this function alone does. So we do not actually need to know exactly what happens at x equals 0. We're asking about the behavior as you get arbitrarily close, as you get closer and closer and closer. Now, it turns out that this is a very peculiar function. As you get, its behavior depends upon whether you're approaching 0 from the left or the right. You have here's the x-axis and here's the y-axis. This is what the function looks like. As you approach from the right side, it gets larger and larger and larger, because as you divide a number by a smaller number, you get a larger and larger and larger result. 1 divided by 0.001 is 1,000, divided by 0.0001 is 10,000, etc. As x gets really, really, really close to 0, this just shoots off toward infinity. Now, as we approach from the left side, it shoots down toward negative infinity. This is a function that we say does not have a limit. And the reason why it doesn't have a limit is because the behavior is different when you approach it from the right as it is when you approach it from the left. It has to be exactly the same when you approach it from the right as when you approach it from the left. Otherwise, we say it doesn't have a limit. So, let's come up with a function that does have a limit. The quantity x plus 1 times the quantity x minus 1 divided by the quantity x minus 1. And we're going to change this, the limit as x approaches 1. This function has a limit at x equals 1. Now, as you can see, if x is exactly equal to 1, then the denominator here is 0, and you cannot divide by 0. So this function actually does not exist at x equals 1, but it does have a limit because its behavior as you approach from the left side and its behavior as you approach from the right side is exactly the same. Now, because we're not interested in the behavior exactly at x equals 1, we can cancel out these two right here. We can cancel out this x minus 1 and this x minus 1. We can cancel those out. You have to be careful about canceling things like that out because you could be dividing by 0, but because the only place that it can be 0 is exactly at 1, and we're not interested in the behavior exactly at 1, we can cancel it out. So, other than exactly at x equals 1, the behavior of this function is x plus 1. Which is the 45-degree angle sloped line, but instead of going right through the origin, it goes through y equals 1 when x equals 0, but it still has the same 45-degree slope. So it's just the same 45-degree slope line translated up. It's exactly parallel to the line y equals x. Now, the only difference between this function right here and the function x plus 1 is right here at x equals 1, the function has a little hole. Exactly at that point, it doesn't technically exist. However, its behavior exactly at that point, its behavior as you arbitrarily approach that point, is the same as the behavior of x plus 1. I said, because we're not interested in its exact behavior at that point, but only as you approach that point, we can say that the limit as x approaches 1 of this function right here is exactly the same as the limit of x plus 1 as you approach that point. So what is x plus 1 at x equals 1?